In this lecture, I want to talk about cosmology and theology. In the centuries following the birth of science, much was learned about the motions of the planets, the constitution of the stars, and the structure of the galaxies. And this was made possible by the development of ever more powerful telescopes, by spectroscopic analysis, and by Einstein's general theory of relativity. And for the first time, the entire universe, spread out in space and time, has become the subject of scientific investigation. And more recently, by applying our knowledge of nuclear and elementary particle physics, we have learned how the universe has evolved from a fiery singularity about 10 billion years ago. Now, what has all this got to do with theology? The traditional philosophical arguments for the existence of a creator do not, of course, depend on particular scientific theories of the universe. They are based on simple, everyday experiences of order in the world and of the dependent nature of material things. Nevertheless, the desire to integrate our scientific and our theological knowledge into a coherent whole often provides an extra scientific criterion for preferring some theories of the universe more than others. Thus, if we believe from revelation that the universe was created at a particular instant of time, we must notice that this is more plausibly brought into coherence with scientific theories that describe the development of the universe from a unique beginning than with those that maintain that the universe has always existed. Thus, Christians might be expected to favor such theories, while those who wish to do away with the need for a creator might prefer the alternative steady state or oscillating universe theories. And such preferences run as hidden and sometimes not so hidden threads through all the scientific discussions of the origin of the universe. When they do surface, they are mentioned as feelings rather than as argued conclusions. Thus Hoyle remarks, "In the older theories, all the matter in the universe is supposed to have appeared at one instant of time, the whole creation process taking the form of one big bang. For myself, I find this idea much queerer than continuous creation." So this is a feeling, not a scientific conclusion. He also found the Big Bang theory unacceptable on scientific grounds because it postulates an irrational process that cannot be described in scientific terms, and also on philosophical grounds because it lies in principle beyond the realm of observation, irrespective of its success. So it simply cannot be a good scientific theory. Under no circumstances ought anything that sounds like a cosmic beginning be acquiesced in by a scientist. This is Hoyle again. Another cosmologist, Harrison, recoiled from the evidence that the universe will keep expanding forever as a horrible thought that would make the whole universe meaningless. So this again is a feeling. Marxist-Leninist writers naturally reject the notion of an absolute beginning as fundamentally incompatible with the principles of dialectical materialism. This does not imply, however, that it is legitimate to argue from a scientific theory to a theological conclusion. Although some Christians have indeed used the Big Bang theory as evidence for creation, others have been more cautious, notably the originator of the theory. And it's interesting to note that the scientist who first put forward the Big Bang theory, and who is now seldom mentioned, is a Belgian Catholic priest, the Abbé Lemaitre. Modern Christian writers on cosmology realize very clearly that it is quite unwarranted to argue from a scientific theory, however successful, to a theological belief. It is always hazardous to make links of this character, as has been found very often in the development of science. Science is concerned with the relationship between one state of the world and another, and it can never provide evidence for an absolute beginning. The real connection is rather different. It is that the basic beliefs of the time tend to encourage or discourage different types of scientific theories, and these may or may not raise different theological questions. Thus, the Big Bang theory inevitably raises the question about what happens before it, whereas the continuous creation theory does not. Now that Christians have realized that it is unwise to argue from the success of the Big Bang Theory to the fact of creation. And agnostics have seen the steady state and oscillating theories, subject to severe criticism on scientific grounds. The arena of argument has shifted. Some theists point to the specificity of the universe as suggesting that it was created purposefully, while agnostics tend to emphasize either its necessary or its random character, and therefore its lack of need for a creator. Historically, cosmology, or the study of the heavens, has played a central role in the development of science. The regular movement of the stars and of the seasons provided an impressive witness to the power and reliability of the Creator. The power of the Creator is emphasized in the words of Yahweh to Job. Can you fasten the harness of the Pleiades or untie Orion's bands? Can you guide the morning star season by season and show the bear and its cubs which way to go? Have you grasped the celestial laws? Could you make your writ run on the earth? Can your voice carry as far as the clouds and make the pent-up waters do your bidding? Will lightning flashes come at your command and answer, here are we? This is all expressed, of course, very poetically, but it expresses the power of the Creator. And Yahweh also demands, where were you when I laid the earth's foundations? Tell me, since you are so well informed. Who decided the dimensions of it, do you know? Or who stretched the measuring line across it? What supports its pillars at their bases, and who lays its cornerstone? As we have seen, the doctrine of creation is the most basic of all Judeo-Christian beliefs, and it affirms that God made the world out of nothing, that he is absolutely distinct from his creation, and that all creation depends completely on him. And this revelation was first given to the Israelites, and their acceptance set them apart from the surrounding idolatrous and pantheistic tribes. The Bible is saturated with the belief in creation, from the powerful words addressed to Job to the confident, matter-of-fact acceptance by the mother of the 7 martyred brothers in Maccabees. We cannot understand the creation of the universe. It is difficult enough to understand creation when it is applied to our own activities. How does a painter create a picture? He has an idea, but to realize that idea, he reorders existing matter. But God created the universe out of nothing. When the painter has finished his work, the picture remains, even if he forgets about it. But the universe depends utterly on God, not only for its initial creation, but for its continuance in being. Without God's sustaining power, it would instantly lapse into nothingness. The created world has its own intrinsic nature given to it by God. Normally, it continues to exist, sustained always by God, and to behave in the way determined by its nature. The material world, the universe, defined as the totality of consistently interacting things, is thus a totally determined system. If we knew exactly its initial state and the laws of its nature, we could calculate exactly how it would subsequently behave. This isn't, of course, possible in practice because we cannot know the present exactly, we don't know the laws well enough, and we cannot do the calculations. This determined development is not, however, a logically necessary development in the sense that it could not be otherwise. God always has the power to intervene, to override the development otherwise determined by the intrinsic nature of the material world. And of course, throughout the preceding paragraph, we are thinking only of the material world, not of man. Man is made in the image of God and has freedom of action, and so is not wholly part of the universe as defined above as the totality of consistently interacting things. It is one of the most astonishing achievements of mankind that we've been able to probe the extremes of the very small and the very large, right down into the recesses of the atomic nucleus and then up to the vastness of cosmic space and time. The observations of the 19th century astronomers showed that our Sun is a rather ordinary star in one of the spiral arms of a galaxy of about 200,000 million stars that we see in faint outline as the Milky Way. Billions of similar galaxies are visible in all directions, and Hubble found that the frequency of the light from them is shifted in a way that shows that they are all moving rapidly away from us. Furthermore, the greater the distance from us, the faster they are receding. In other words, all the galaxies are moving in just the way we would expect if they had all come from a mighty explosion at a time that we can calculate to be about 10 or 15,000 million years ago. This figure is subject to considerable uncertainty, not only due to the inevitable difficulties of measurement, but also because it assumes that the expansion is uniform. It has also been suggested, as we shall see later, that in the early stages there was a period of more rapid expansion. A deeper understanding of this expansion was provided by Einstein's general theory of relativity. His cosmological model was shown to lead to the observed expansion, and Lemaitre derived from it the measured velocity of recession of the galaxies. For the first time, the universe as a whole became an object of scientific study. Thus, theory and experiment combined to support the idea that what we now see is an aging universe, the scattered ashes and sparks that are remaining from the compressed incandescence of its fiery beginning. Several other lines of evidence, such as the motions of clusters of galaxies and the relative proportions of various types of nuclei, also give about the same result for the time when all the matter of the universe was concentrated in a small volume. We can apply the laws of physics to understand many of the processes occurring during the expansion of the universe from this initial compressed state. But at present there seems no possibility of finding out by scientific means what happened before the expansion began. It seems to be the ultimate limit of science, a limit that some have ventured to call the creation. It must, however, be emphasized again that this is not a scientific inference. It is not possible to show scientifically of any state that there can be no antecedent state. We cannot exclude the possibility that there was a previous state, perhaps one of contraction. It has been suggested that the universe is eternal, either remaining always more or less the same on a sufficiently large scale, or perhaps alternately expanding and contracting. And now we want to discuss these theories in more detail. Several lines of evidence, as we've mentioned, indicate that the universe has expanded from a compressed state about 10 or 15 billion years ago. So this suggests that the development of the universe is a continuous progression from an explosive beginning to a silent end. The processes occurring in the first few instants of the expansion have now been reconstructed in considerable detail, making use of the latest knowledge of nuclear and elementary particle physics. The details are still highly technical and somewhat speculative in some respects, for the very earliest times, namely the first fraction of a second. The evolution of the universe from about 1/100th of a second from the beginning of the expansion onwards are much better understood. And during that time, the universe expanded and cooled rapidly, and the elementary particles combined to form hydrogen and helium. And inside the stars, it became possible to build up heavier nuclei. And this could not happen before because nuclei with 5 or 8 neutrons or protons are unstable. Inside the stars, however, intense gravitational pressure allowed the hydrogen and helium to combine to form the heavier nuclei. The nuclear reactions taking place at that time have been studied in laboratories, and so we can calculate the proportions of the different chemical elements in the universe. This is very similar to what is observed, showing that we have a detailed and quantitative understanding of the processes that took place so long ago. So all the nuclei that constitute our own bodies were in fact constituted into their present form in the interior of stars, so you can say that you're all made of stardust. About 10,000 million years later, the evolution of living beings took place, among them men and women who are able to understand and reconstruct the details of the processes that made our existence possible. Now, how do we know that all this story is true? Some parts of it, of course, are much better understood than others. and research is continually providing more details of the various stages, even of the processes occurring in the first hundredth of a second. As already mentioned, the formation of nuclei is quite well understood, and the results of calculations agree with the measured abundances of the various chemical elements. Additional confirmation came from the observation of what is called the cosmic microwave background radiation. At the stage of the formation of the atoms, all the electrons were captured by nuclei, and thereafter the photons no longer interacted strongly with the rest of the universe. These photons, or atoms of light, were in statistical equilibrium with each other, and their energy distribution is related to their temperature. This energy distribution is well known from the early days of the quantum theory and is given precisely by Planck's formula. As the universe expanded, the temperature fell, and with it the average energy of the photons. Since we know the temperature at the time when the matter and radiation were decoupled, we can calculate the initial energy distribution of these photons, and also the way that temperature falls as the universe expands. These photons are still present in the universe, and now their temperature is just about 3 degrees above the absolute zero of temperature, and photons of this temperature are in the microwave region. At the same time as these calculations were being made in Princeton, this microwave radiation was actually observed in 1965 by Penzias and Wilson. These two radio astronomers were hoping to measure the radio waves emitted by our galaxy, but first they had to make sure that there was no spurious noise in their detecting antenna that could mask the signals they were looking for. And they found that however they turned their antenna in different directions, they always detected some radiation, and furthermore it came with equal intensity from all directions, and so could not come from our own galaxy. It must come from the universe as a whole. It was then realized that this was probably the radiation left over from an early stage in the evolution of the universe. Since then, the microwave background radiation has been studied in detail, and in particular, it has been shown to have the spectral distribution closely similar to Planck's formula, and to come almost equally from all directions. It is just what would be expected from the theory of the evolution of the universe, and provides a compelling verification of its truth. The very slight departures from isotropy that have been found quite recently are just what are needed to allow the formation of galaxies. Another prediction of the theory that can be experimentally verified is the proportion of helium in the universe. The helium is formed at an earlier stage than the heavy elements, and so its proportion is a sensitive indication of the relative numbers of the nuclear particles and the photons. And this ratio, in turn, fixes the temperature of the microwave background radiation. Thus, from the measured temperature of 3 degrees, it can be estimated that the proportion of helium in the matter from which the stars were formed must be about 25% by mass. And this is just the same as the value for the hydrogen-helium ratio obtained from theories of stellar evolution. It is worth noting at this stage the extreme specificity of the whole process, a feature that will be returned to later on. In particular, the ratio of nuclear particles to photons, electrons, and neutrinos must be about 1 to 1,000 million. If there were more photons, the number of neutrons and protons will remain about the same, so that as soon as the temperature falls low enough for helium to be formed, they will all combine in this way. Then nearly all the nuclear particles will become helium, and then it is not possible to build up any of the heavier nuclei. On the other hand, if there are fewer photons, the interaction that keeps the number of neutrons and protons the same will cease too soon, and before the helium formation can begin, most of the neutrons will have decayed to protons. Nearly all the nuclear particles will then be protons, and so not enough helium can be formed to lead to the production of heavier nuclei. Thus the ratio is extremely critical. If it is too large or too small, there can be no nuclei heavier than helium, and so no possibility of life. Carbon is essential to life, and like the other heavy elements, it has to be made inside stars by a series of reactions starting from hydrogen and helium. The chain of reactions starts from the alpha particle, that is the nucleus of helium, and two of them can combine to form beryllium-8. Then another particle is added to give carbon-12, and another to give oxygen-16, and so on. But for this to produce carbon-12, several conditions have to be satisfied. If beryllium-8 were stable, the process would proceed so explosively that the star would be blown apart, and the synthesis of heavy elements would be impossible. Fortunately, however, beryllium-8 is just unstable, so this doesn't happen. But then it is difficult to see how carbon-12 can be formed. Beryllium-8 has an extremely short lifetime, and so if carbon-12 is to be formed, another alpha particle must collide with it before it decays. The collision of three particles is a very rare process, and so the reaction rate is so small that any carbon formed in this way would soon be transformed into oxygen. The only way the carbon-forming reaction could occur more rapidly is if there is a state in carbon-12, an excited state, just above the threshold at 7.65 MeV, and that would make possible a resonance reaction. Now Hoyle was thinking about all this and seeing how carbon could possibly be formed, and so he looked to see whether there was indeed such a state in carbon-12. He looked up the tables of nuclear states that physicists have built up over the years, and he found that no such state existed. So he suggested to experimentalists that they should look for it, and they of course laughed at him and said this was not very likely that the state should have been missed. But he pressed them and then said, well, perhaps we shall look again. And they did look again, and within a few days the state was found at just the predicted energy. So this is quite an extraordinary, call it coincidence or call it design, as you wish. Now the formation of carbon-12 also requires that it is not all transformed rapidly into oxygen by the addition of an additional alpha particle, and this would happen, of course, if there was a state in oxygen-16 around the threshold energy. There is indeed such a state, but its energy is 7.12 MeV, which is just below the threshold at 7.19 MeV, and for this reason the reaction cannot take place. Thus, the possibility of the formation of carbon-12 depends very critically on the energies of three states in beryllium-8, carbon-12, and oxygen-16. Now, is this just a coincidence, or was it planned? Now, this discovery astounded Hoyle and led him to consider profound questions such as whether the laws of physics are deliberately designed to permit the existence of life, or whether the existence of life is the result of a set of freakish coincidences in nuclear physics. It's very interesting to reflect that our being here at all depends on the energies of just a few states in some nuclei. If they were slightly different, we wouldn't be here at all. And all this is connected with arguments about what is called the anthropic principle that will be discussed later on. Now, a serious difficulty of the Big Bang theory concerns the mass density of the universe, which determines whether the universe will go on forever expanding or eventually slow down, stop, and then begin to contract again. The density corresponding to the behavior at the dividing line between these two possibilities is called the critical density. And calculations show that what happens depends extremely sensitively on the mass density near the beginning of time. Indeed, at 1 second after the Big Bang, the mass density must have equaled the critical density to an accuracy of 1 part in 1,000 million million. If the mass density were outside these limits, the universe would either collapse or expand so rapidly that there would be no time for the development of life. And does this have a rational explanation? It was also found that calculations of the density of magnetic monopoles using the well-supported grand unified theory showed that they should be as numerous as protons and neutrons. But since the monopoles are very massive, they would then exert such a strong gravitational attraction that the universe would rapidly collapse. A further difficulty was posed by the extreme uniformity, to 1 part in 100,000, of the temperature of the cosmic microwave background radiation. Such uniformity could only come about by strong energy-sharing interactions, and yet the parts of the background radiation are too far apart from this to happen due to the expansion of the universe. Now, the solution to all these problems finally came from the concept of the inflationary universe developed from 1979 onwards by Alan Guth. In the very early stages of the Big Bang, the universe is driven to a stage of very rapid expansion by the repulsive gravitational field due to what is called the false vacuum. Before this expansion begins, thermal equilibrium is established, and this is retained during the expansion, thus solving the uniformity problem. The production of magnetic monopoles is reduced by the supercooling of the delayed phase transition. The process also automatically drives the mass density to the same value as the critical density. The very small perturbations that remain are just what are required to lead to the formation of stars, galaxies, and clusters of galaxies. Thus, what appeared at first to be an astonishing coincidence or a serious problem all received a rational explanation within the inflationary model, although it must be added that this requires the initial parameters of the model to be assigned values in quite narrow range. In the years since Guth's proposal, many varieties of inflationary theories have been developed, and these are still the subject of intense debate. The general idea is very probably correct, but the details have still to be established. One of the difficulties of cosmology is that there are many imaginative and speculative theories, but rather few experimental observations that enable them to be tested. The situation in this respect is now greatly improving, and new satellites, scheduled to be launched in the years 2000 and 2004, should provide even more accurate data and correspondingly sharp tests of cosmological models. The whole story shows in ever more detail the extraordinary way the universe has developed from the initial singularity to its present state, and it is the ongoing task of the scientists to explore this in every way possible. It is also clear that it is always unwise to ascribe any cosmological event, however improbable it may seem, to the direct action of the deity. So often it is later found to be entirely explicable by a new theory. As an alternative to the Big Bang theory, Bondi and Gold, and also Hoyle, proposed the steady-state theory. This was based on what they called the perfect cosmological principle, which says that on a sufficiently large scale, the universe is always the same, both in space and time. In particular, the number of galaxies in any large volume of space is constant. Since, however, we know that the galaxies are receding from each other, this can only be ensured if new galaxies are coming into being to replace those that are moving away. So they therefore postulated that hydrogen atoms continually appear out of nothing and ultimately condense and coalesce to form new galaxies at a rate just sufficient to replace those lost by recession. The rate of appearance of the hydrogen atoms comes out to be so small that there is no possibility of ever observing it, just one hydrogen atom per year in every cubic mile of space. The motivation behind this theory was avowedly to provide a rival to the Big Bang theory, which, although it doesn't prove that the creation in time has occurred, yet seems more consonant with it. And to do this, they were obliged to postulate what they call continuous creation, and yet they resolutely refused to consider how this creation occurred, or to attribute it to a creator. It thus seemed to be a very gratuitous hypothesis, and yet they were correct to maintain that it is a legitimate scientific theory that stands or falls when its consequences are compared with observational data. The observation of the 3 degrees background radiation by Penzias and Wilson provided strong evidence against the steady-state theory, since it shows that the present expansion of the universe started some 10 or 15,000 million years ago. On the steady-state theory, we wouldn't expect this background radiation to be there. The redshifts of quasi-stellar objects are also inconsistent with the theory, and for these reasons the steady-state theory has now been abandoned, and scientists reluctant to envisage the possibility of a creation turn their attention to the possibility of an oscillating universe. At present, the universe is expanding, but the question is whether it will go on expanding forever, the galaxies and the stars getting colder and colder, or whether at some epoch the expansion will slow down and go into reverse, leading eventually to the collapse of the universe again into a very small volume. If the universe is ultimately destined to collapse, we can then see the present expansion and collapse as possibly just one of a whole series of expansions and contractions going on forever, a spectacle that banishes the possibility of a creation at a particular instant, but not, of course, it must be added, the need for a continuing sustainer of the whole oscillating process. This question is physically the same as asking whether a rocket fired upwards will escape from the Earth's gravitational field or eventually fall back to the ground. And we can answer it in two ways: by examining the way the velocity of the rocket is changing after the motors have been switched off, or by comparing the velocity at that moment with the velocity that we can calculate to be sufficient to take the rocket out of the Earth's gravitational field. And when we apply this test to the receding galaxies, we find that we cannot yet measure the velocities of recession at great enough distances to determine whether they are on the road of eternal expansion or the road of eventual contraction. We therefore have to fall back on the second method, which requires a knowledge of the total mass of the universe. We can calculate the mass the universe must have if its gravitational attraction is to be sufficient to slow down and ultimately reverse the recessional motion of the galaxies. If this mass is greater than the actual mass, then the expansion will go on forever. But if it is less, then the expansion will ultimately turn into a contraction. Present estimates of the mass of the universe show that it is between 10 and 100 times too small to reverse the motion of the galaxies. This has led to a hunt for what is called the missing mass, particularly among those with a vested interest in an oscillating universe. It is possible that there is a halo of unseen mass around the galaxies, and the neutrinos may account for some more. But even then, the best estimate is that only about 1/10 of the required mass can be found. This is, of course, open to revision in the light of further research. However, it is worth noting that it is remarkable that the masses are so closely the same, and this may well have a deeper significance. There are other difficulties with the idea of an oscillating universe, in particular those connected with the second law of thermodynamics, which requires the total entropy of any system to increase continually. And as Tolman has showed, when this is applied to an oscillating universe, the result is that the amplitude of the oscillations becomes less and less, so eventually it all runs down. Thus the second law of thermodynamics appears to exclude the possibility of an oscillating universe. Thus at present there are considerable difficulties with the theory of an oscillating universe, but it cannot yet be entirely ruled out. It is always possible that further developments will weaken the arguments mentioned above, and scientifically it remains an open question. Philosophically, an eternal universe is open to the objection that if we are in such a universe, then everything would already have happened an infinite time ago. The only way to avoid this conclusion is to say that the whole of history is indeed repeated in all its details an infinite number of times. The periodicity of this repetition need not be the same as that of the universe as a whole, providing it is equal or greater. Such a belief in an oscillating universe has indeed often occurred in human history, but in our civilization, as we have already seen, this idea was rejected because the incarnation of Christ is a unique event that cannot be repeated. God's plan in history is a linear one from the beginning to the end, and is incompatible with eternally recurring cycles. And that is why the Church has always believed in creation in time, and conversely it is notable that belief in an oscillating universe is always one of the hallmarks of atheism. So with the abandonment of the steady-state theory and the uncertain future of the oscillating universe theory, those who are unable to accept the idea of a creator have turned their attention to developing the concept of a necessary universe, that is, a universe that must be the way that it is. If the universe is necessary, then there is no need to inquire why it is the way that it is. It couldn't be otherwise. And so there's no need to look for an explanation. In particular, no need for a creator, or so the argument runs. The idea of a necessary universe has a long history going back to Aristotle. As a scientific hypothesis, it encourages the idea that it is possible to obtain the whole of science, including even the values of the fundamental constants, by pure deductive reasoning. There is then no need to make experiments. Physics, like mathematics, may be carried out by thought alone. And strenuous efforts along these lines to develop such a theory were made by Eddington, but in spite of instructive insights, he did not succeed in his endeavours. The structure of the universe is far richer and more sophisticated than could ever be imagined by our minds. But even if it's not possible to discover the structure of the world by thought alone, it remains possible that it is a necessary world. Due to the limitations of our minds, we might need the help of experiments to understand the order of the universe, and then we could realize that it is in fact a necessary universe. The experiments then just serve as intellectual scaffolding that can be discarded when we have reached our goal. There are indeed many features of the universe that might seem at first to be given, but which turn out on further examination to be necessary. For example, the number of spatial dimensions must be 3, for otherwise the solar system would not be stable. As science advances, more and more features of the world seem to be linked together, and not at all arbitrary. Indeed, the aim of theoretical physics is the unification of our knowledge of the world, expressed inevitably in mathematical terms. Already the unification that has been achieved is remarkable, and areas of experience that seem to be quite distinct are now seen to be but different manifestations of the same underlying order, as for example electricity, magnetism, optics and radio are all governed by Maxwell's equations. Great efforts are being made to unify the 4 fundamental forces of nature, and important progress has already been made. It's quite possible that scientists will eventually succeed in developing a comprehensive theory that explains all phenomena and enables the results of all conceivable experiments to be calculated. Even this, however, will fall short of proving that the universe is a necessary one as a consequence of a theorem of the mathematician Gödel, who showed in 1930 that no set of non-trivial mathematical propositions can have its proof of consistency within itself, and that there are always meaningful propositions that cannot either be proved or disproved within the system. Thus, any scientific cosmology, which is necessarily expressed in mathematical terms, must fall short of being a theory that shows that the world must necessarily be what it is. There is always the possibility of the surprising, the unexpected, that points beyond this world for those who have eyes to see. Now, the more closely scientists study the evolution of the universe, the more evidence they find of its extreme singularity. And several examples of this have already been quoted. If the proportion of nuclear particles, for example, and photons had been slightly different, there would have been nearly all hydrogen or nearly all helium, and in each case no heavier nuclei, and so no possibility of life. Again, it has been noted that the universe is remarkably homogeneous on a large scale, and this is the result of the initial conditions. It is very difficult to understand why these inhomogeneities should be so small, and yet if they were any larger, the matter of the universe would have collapsed into black holes long ago, while if they had been any smaller, there would have been no galaxies. The evolution of the solar system is also highly specific. There is still no satisfactory theory of how the system of planets was formed, and in particular how they came to be rotating about the Sun in nearly circular orbits and nearly in the same plane. Yet it is only on a planet of a certain size moving on a nearly circular orbit that life could have evolved. The more this evolution is studied, the more we realize that it is immensely improbable that we should be here at all. We have come to where we are on an exceedingly narrow track. We always naturally tend to think that we are the center of things. The ancient Hebrew cosmology, the cosmology of the Greeks, and the cosmology of the Hindus all put man at the center of the universe. In Genesis, man appears as God's supreme handiwork on the sixth day, and all creation is his to dominate. This anthropocentric picture received a crushing blow when Copernicus showed that the motions of the planets can be much better understood if they rotate about the sun. So now the sun is the center, and the Earth a rather small planet revolving around it. Man's centrality received further blows when it was shown that the sun, so impressive to us, is a rather undistinguished star near the end of one of the spiral arms of a vast galaxy of billions of such stars, and that this galaxy itself is one of many billions of similar galaxies scattered throughout an unimaginably large universe. So what then remains of the centrality of man and of the world made for him by God? Compared with the vastness of space, we are totally insignificant. We can be filled with awe and reverence, and with the psalmist we can rejoice that the heavens show forth the glory of the Lord. Or with Pascal, we can be terrified by the vastness of space, realizing that man is but a reed, the most feeble thing in nature. The entire universe need not arm itself to crush him. A vapor, a drop of water, suffices to kill him. It is true that we can reply, again with Pascal, that man is a thinking reed. If the universe were to crush him, man would still be nobler than that which killed him, because he knows that he dies, and the advantages the universe has over him, and of this the universe knows nothing. But how can we be sure even of this? Is it not very likely that around some other stars in faraway galaxies there are sentient beings and civilizations immeasurably superior to our own, who know what we are doing and regard our activities in much the same way as we regard those of ants and bees? There are indeed few grounds for pride when we consider our position in the universe. And if there is no other life in the universe, it raises another question posed by Margaret Knight, a well-known humanist, when she said, "If life is the purpose of creation, what conceivably can be the point of countless millions of lifeless worlds, or the aeons of astronomical time before life existed?" The Church, she added, has glanced uneasily at these questions, but it has never answered them. And in saying this, she was but echoing Maimonides in his Guide for the Perplexed, when he said, "Consider then how immense is the size of these bodies, and how numerous they are. And if the earth is thus no bigger than a point relative to the sphere of the fixed stars, what must be the ratio of the human species to the created universe as a whole? And how then can any of us think that these things exist for his sake, and that they are meant to serve his uses?" Now, however, when we know far more about the universe, when we begin to understand in a very detailed way the evolution of the very matter of which it is composed, we begin at the same time to glimpse a new truth, namely that it looks more and more as if the universe was indeed made just for man. At each stage in its development, there seem to be many possibilities, and every time the one is chosen that alone leads to a universe that can produce man. Within this perspective, the insignificance of man takes on a completely different aspect. We wonder at the vastness of the universe in space and time compared with the smallness and frailty of man. Why this apparent prodigality? And now we see the answer. All this stupendous evolution was necessary in order that the earth should be made as a habitation for man. The process of nuclear synthesis, by which the elements constituting our bodies are built up in the interior of stars, takes billions of years. And in this time, the galaxies containing these stars will inevitably move vast distances from their point of formation. So the universe must be as large and as old as it is, in order that it can be prepared as our home. And so this is why we can say in the end that it is our universe. Freeman Dyson has summed this up in the words, "As we look out into the universe and identify the many accidents of physics and astronomy that have worked together for our benefit, it almost seems as if the universe must in some sense have known that we were coming." The idea that the universe has taken just that path in its evolution that leads to man is called the anthropic principle. It must be noted that this principle doesn't explain why the universe evolved in this particular way, unless we already believe in a creator who intended this result. Since we are indeed here, then of course the universe must be such as to allow our emergence. If the universe had, so to speak, taken the wrong turning, then we wouldn't be here to talk about it. Or perhaps there have been millions of different universes in non-interacting spaces, and this is just the one that happened to be such as to allow for the evolution of man. It's sometimes been objected that the anthropic principle is not scientific because it is not testable and leads to no new discoveries. However, the work of Hoyle about those states in beryllium-8 and in carbon-12 and in oxygen-16 provides one example where the anthropic principle did lead to new scientific knowledge. There is an even stronger form of the anthropic principle that deserves mention. We are accustomed to think of the constants of nature, like the velocity of light or the mass of an electron, as fixed and unalterable. Now, the strong form of the anthropic principle says that the values of these constants are in fact fixed by the requirement that the universe will allow man to evolve. Some rather detailed arguments have been made to support this idea. So this raises the possibility that there are many universes with different values of the fundamental constants, and only those with the values that we know can produce man. There is, however, a difficulty with this argument. The number of fundamental constants is about 10, whereas the number of conditions they must satisfy is substantially greater. So this implies that it is not possible, even in principle, to fix the parameters so as to ensure the evolution of man. There's just not enough of them. The values of the constants cannot then be a result of a random process, and so the universe is our universe at the deepest level. It should also be remarked in connection with the anthropic principle that it is possible that when science advances further, we shall see that what appear to be arbitrary choices in the evolutionary processes are in fact necessary. That, for example, we might find that the ratio of nuclear particles to photons must be as it is, and similarly for the other apparently very singular parameters. At an even deeper level, the very values of the fundamental constants, as we know them, might be necessary values, as indeed Eddington tried to show. And this would make it even more surprising that we are here. Although the emergence of life in the universe seems to be a most improbable process, there are so many stars that might conceivably have planets on which life could have evolved that there have been many speculations that conscious beings, and perhaps well-developed civilizations, exists in many parts of the universe. And this has led to ambitious schemes to detect signals that may have been broadcast by such beings, and also there have been plans to transmit signals of our own. However, until we have factual evidence, the whole subject is highly speculative, serving to distract attention from real and solvable problems. There have recently been many speculations about the possibility of providing a scientific explanation of creation itself. The first difficulty is to know whether the laws of physics still apply. It is always possible to invoke the power of God, but it is the duty of the physicist to try to solve problems by scientific methods alone. Thus, it might well be thought that creation requires the violation of the conservation laws, but it seems that this is not necessarily the case. There is no difficulty about the total electric charge and angular momentum, since these have values consistent with zero for the universe as a whole, and the total linear momentum is not definable. The main problem concerns the principle of conservation of energy, and it was then realized that the negative potential energy of the universe could exactly balance its positive kinetic energy, so that the total energy of the universe is just zero, so that there is no need for God to override the conservation laws during the creation of the universe. Vilenkin has suggested that the universe could come into being by quantum tunneling from nothing. This assumes that quantum mechanics can be applied to the whole universe, an assumption that rests on a discredited interpretation of quantum mechanics, as we've seen in the previous lecture. Hawking has suggested that time, like space, has no boundary. There is thus no initial singularity, no moment of creation. Thus, to quote him, the boundary condition of the universe is that it has no boundary. The universe would be completely self-contained, and not affected by anything outside itself. It would neither be created nor destroyed, it would just be. This proposal has the merit that it does not require an initial singularity where the laws of physics break down. However, he also supposes that if there is no beginning, then there is no need for a creator. And this is a misunderstanding of the nature of creation, which is the causing of existence, an activity that is continuous. The continuation in existence requires God's causal agency just as much as the initial beginning. So even if there is no initial singularity, the creative act of God is still necessary. And it should be remarked that the physicist's conception of a vacuum is quite different from that of the theologian. For a physicist, a vacuum is rich in potentialities, but even then it requires an external agency to cause anything to happen. The theologian's vacuum is absolutely nothing at all, no matter, no space, no time, and no potentialities of any kind. From that nothing, nothing can come. The physicist's vacuum, however, needs to be created. Some attempts have been made to give a scientific account of creation out of nothing by a chance process. And chance is referred to as if it is a causative agent, not as indicating unknown causes. There is a more general difficulty. All a scientific theory can really do is to say that if there exists matter with such and such properties that obeys certain equations, then if it is then started off in a particular configuration, it will behave subsequently in a way calculable from those equations. What it cannot say is whether there indeed exists matter with such and such properties, and how it is put into a particular configuration and no other. As Hawking asked, what is it that breathes fire into the equations and makes a universe for them to describe? And who sets the initial conditions? Furthermore, a scientific theory is only reliable in the regions where it has been thoroughly tested. When it is extrapolated to other regions, its predictions must be less certain. And what is more unpredictable or more singular than the moment of creation? Another point worth noticing is the way that creation is associated by some scientists with the very simplest structures. Thus, Atkins has remarked, the creation can generate only the most primitive structures, structures of such simplicity that they can drop out from absolutely nothing. But it must be said that, simple or complicated, small or large, the passage from non-existence to existence is the most radical of all steps. It cannot be glossed over, and no one with any sense of ontological reality could accept this for an instant. However large or small the object may be, the passage from non-being to being is the greatest possible transition. We are talking about creation itself, and that is an activity that belongs to God alone. So to conclude, cosmology remains highly speculative, with many new theories, but insufficient data to test them thoroughly. One of the most recent is the instanton theory proposed by Hawking and Turek. An instanton is a sort of lump which covers gravity, space, and time together. It is a twist in matter and space-time. It forms the rounded top of the space-time cone at the initial singularity of the Big Bang. In this region, the distinction between space and time is blurred. The authors of this theory have been asked what are the implications for the existence of a creator, and have replied that there are none. However, they add, with remarkable confidence, that if a divine being wanted to create a universe, the simplest way to do it would be to use our instanton. Following the COBE satellite in 1992, the microanisotropy probe is scheduled to be launched in 2000 and the Planck Explorer in 2005. And these should provide extensive data to test the wide range of current cosmological speculations. Turek has commented that cosmology is on the threshold of turning into a science and is confident that an understanding of the beginning of our universe is within sight. All these scientific developments show in ever-increasing detail the awesome extent and wonderful complexity of our universe. Beneath this complexity, we are finding a unified structure, so that the discoveries of nuclear and particle physics can enable us to calculate in detail the processes that took place billions of years ago, and eventually spread out over unimaginable distances. Thinking about this can increase our reverence for the power of the Creator. However, as many examples have shown, it is always unwise to base any arguments for the existence of God on particular scientific results. Very often, what has seemed at first sight to have been a remarkable coincidence, suggesting a supernatural cause, has been shown by further work to be entirely explicable by the laws of physics. So the story of our attempts to understand the universe thus shows a complex interaction of theological beliefs, scientific observations, and theoretical speculations. It is notable that it was Christian theology that made science possible in the first place, and with it all the vast development that has led to our modern understanding of the universe.